fields, this is a really important concept in this course, mostly because we want you to know how to follow axioms in math. Axioms are basically rules you have to follow. Like, you don't have to check if they're correct. It's just like some rules we made in math that you have to follow. So the field axioms, there are a few things you need to be careful. One is, well, a field has two operations. One is addition, one is multiplication. Remember that when we talk about the two operations, they might not be the usual operations you've been using for the past, close to maybe 18 years. I don't know how old you are, but they might not be the usual addition and multiplication. It could be something weird that some of you might have seen. For example, in fields with 4 elements, we have 1 plus 1 equals 2, 0, which is not what you are familiar with. So remember, we have two operations, addition and multiplication, but we can define them in different ways. Anyway, next is you have to special distinguish the elements 0 and 1. Distinguished means that 0 cannot be 1, okay? They have to be different, which means a field will have at least 2 elements, 0 and 1. So the smallest field you can have is a field with 2 elements, 0 and 1. This is the smallest field. Remember, distinguished means 0 cannot be 1. Okay? That's the first sentence, and then we have closure. Closure means that if you add 2 elements in the field together, you still get elements in the field. If you multiply them together, you still get elements in the field. So I'm going to use this to tell you some of the sets that are not fields, so we can use it as counterexamples. So for example, the set of integers is not a field. This is not. Maybe I should write it like this. So set of integer is not a field. Okay, this one is not because it failed closure or anything. It's closed under addition and multiplication. Maybe I should do something else. Let me use this one instead. For example, the interval 0, 2. Okay, this is not a field. Why? Well, it has 0 in there. It has 1 in there. However, it's not closed under addition. For example, 1 is in the set, right? 1 is in the set, but 1 plus 1. So 1 is in the set, 1 is an element, plus another element in the set equals to 2, but 2 is not in the set. So this shows that, well, it's not a closed under addition, so it fails the closure axioms. There are many other ones, for example, let me think. The irrational numbers, the set of irrational numbers. So let me use another color. So we denote the set of irrational numbers as this. So real numbers remove rational numbers is a set of irrational numbers. Set of irrational numbers, okay? This is also not a field. Well, it filled multiple axioms, but it's not closed under addition. For example, let's say root 2 is in the set, right? And negative root 2 is also in the set. But if you add them together, you'll get 0, which is not in the set. Well, you can see that the irrational numbers fail to be a field directly because, well, it doesn't even have 0 and 1 either. Okay. So, but you know that, well, it's not closed under addition. So that can give you some idea of what closure means. Associative associative basically means that, well, you can switch order. Not really switch order. I mean, switch order would be cumulative, but associative is you can add brackets basically. So you can do those two first, or you can do those two first. Similar for this. So for example, let me think if there is anything that's not associative. Sorry, just give me a moment. Can't think of any. Like the ones you've seen so far are mostly associative. But let me just explain what's associative. So for example, 1 plus 2 plus 3. You can first add those two together. This is equivalent to 1 plus 2 plus 3. Right, so that means, well, it's associative. You can change the plus to multiplication as well, and you'll see that they're equal, so they are associative. Commutative means that, well, this time you can actually switch order. So x plus y equals to y plus x, which means like 1 plus 2 equals to 2 plus 1. 1 times 2 equals to 2 times 1, something like that. So that means commutative. Identities, this is a important one, so I'm gonna put the star here, really important. The first one is called additive identity of the field, which means that if you have 0 plus x equals to x, so something plus your element equals to the element itself, then it's called additive identity. What I want to mention is 0. Okay, 0 is more likely a symbol for additive identity. We are not saying it's always 0, the number is 0. It's mostly just like a symbol for us in this case. Sometimes your additive identity is not necessarily the number 0. Okay, not necessarily, not always. This is not always true. Well, in number field, yes, this is true. I'll talk about number field in a moment, but it's not always true in all cases. So remember, 0 and 1, they are not necessarily the numbers. They're just additive identity and multiplicative identity. 1 means you have to, if you add it, you get back to your original element. The other one is if you multiply it, you get the original element. That's identity. Inverses. We have additive inverses and multiplicative inverses. Remember, for additive inverses, it's any x. So every single element in the field should have additive inverse, which means that if you add your additive inverse to the original element, you'll get back to 0. Again, this 0 is just like it just means additive identity. It's not always a number 0. That's what I want to say. Not always. So we usually denote the additive inverse as negative x, but don't think of it as actually the negative number because it's just a symbol. Okay, it's just a symbol. We're not actually talking about the negative numbers. It's not always true. Yeah, anyway. Just like 0 and 1. We're not talking about the number, we're talking about additive identity, multiplicative identity. Here, we're not talking about number either. We're talking about additive inverse and multiplicative inverse. For multiplicative inverse, there is something you have to remember that only non-zero element has multiplicative inverse. So if we're talking about 0 or the additive identity, then you don't even have an inverse. Okay, you don't have an inverse. This is important because you might lose mark. Why? Because whenever you want to use, so in question, let me write it down. In question, if you want to use multiplicative inverse, you should mention that you need to mention it's non-zero. It's because it's non-zero, so you need to mention this. To mention, since x is not zero, x inverse exists. Okay, make sure you have this because you might lose a mark if you don't. The last one, distributive, I'm pretty sure I don't really need to explain what it means. You've been using it for the last 17, 18 years. So that's all the axioms, field axioms. I don't know if this makes sense to you or makes sense to me, because, well, I took this course a long time ago and I've been TAing, and I even TA'd the 4th year course that's based on fields. So this is, I'm very familiar with this. Maybe you cannot say the same, so, well, go get help, watch videos, ask the other people, make sure you actually know them, make sure you know all the axioms, make sure you know their name, just know them by heart, you know. Another 2 things you should know besides the field axioms are claim 2.3.2 and 2.3.3. The first one is any of the elements in the field multiplied by 0 will give you 0. This is not one of the axioms, but you can use it directly because it's a claim in your textbook. Next is if you have a field with 4 elements, then A times B is 1. Again, this one is not one of the field axioms, but you can use it directly because it's a claim in your book. Remember, this is for 4 elements, so if you have a field with 2 elements or 3 elements, or even more like 5 elements, you cannot use it, okay? This is strictly for 4 elements. Now, let's look at example 2. Using regular addition and multiplication of numbers, which of the following sets is a field? Regular addition and multiplication of numbers. What does this mean? This means the usual addition and multiplication you've been using for the last 18 or 17 or 20, I don't know how old you are. For the last many years you've been, as a student, you nerd in math, okay, which means, well, 1 plus 1 is not 0, it's 2. So using those, which of the following sets is a field? I think I mentioned in the tutorial that there is a really fast trick to tell this, so I'm going to introduce a new idea which you will not learn in this course and you cannot use it directly, but if you want to use it to tell if they're fields or not, it's useful, so I'm going to tell you. Here is a claim. The smallest number field is the set of rational numbers. What is number field? Number field means the subfield of R. So subfield of R of real numbers. What does subfield means? It means it's a subset of real number, and 2, and the operation is the usual regular addition and multiplication. So the one you use in real numbers. Regular addition and multiplication. Why is this useful? So what I'm saying is anything that's a subset of a real number and smaller than the set of rational numbers, and we're talking about regular addition and multiplication, they're all not a field. Okay, they are all not a field. Why is this helpful in this case? Because, well, if you look at those, let's see. First of all, R intercept the set of integers would give you the integer. Integer is definitely smaller than Q, so it's not a field. What is this? This is an interval. Okay, it's a subset of real number, and we're talking about regular addition and multiplication. So it satisfies this. Well, is it smaller than Q? Yes, obviously. Okay, it doesn't include all. I mean, I don't want to say it's smaller than Q, but it doesn't include all elements of Q. It's not smaller than Q. It just doesn't include all elements of Q. So it's not a field. You understand what I mean in chapter 5. Next, the set of n over 3 where n is an integer. Well, do you think it includes all elements of Q? Well, obviously no, so it's not a field. Next, we have this. Well, clearly this is a subset of integers, right? It's a subset of integers. It does not include every single element in Q, so it's not a field. And lastly, we have Q union the set of integers, which is going to give you Q. And they said Q is a number field, which means it's a field. So it is a field. See how fast it can give you the answers, although you need to prove it. So you can not really use it directly. You cannot say, oh, Lin said the smallest number field is Q, so those are not field. Cannot use it like that, but it can give you some answers. So that's how I did it so fast. But we'll talk about the counterexamples and show how to prove. Right, let's go back and look at each of the set we have. First of all, the set of integers, I think I just mentioned before. Oh, never mind, not there. Set of integers. Whenever I see integers, usually I think about inverse. Usually they do not have multiplicative inverse. Okay, either it's integer or subsets of integer. I always think about the inverse. So this one, for example, 2 has no inverse. No multiplicative inverse. Multiplicative inverse. Why? Because 2 times 1 over 2 is going to give you 1, right? But 1 over 2 is not in the set of integers. So that's the first one. The second one, didn't I do the second one already? Yeah, the second one is here. It's not a field because 1 is in there, but 1 plus 1 equals to 2 is not there. Basically this, okay? Oh, 1 is in there, but 1 over. So this one fails, it's a field closure. Number 3. As I mentioned, okay, this, it looks like irrational numbers, right? But it's restricted because, well, the bottom has to be 3, right? Which means, well, let me use another color. Which means, for example, 2 over 3 is in this, but it's reciprocal, but 3 over 2 is not in there. We know that 2 over 3 times 3 over 2 is 1. So that means 2 over 3 has no multiplicative inverse. Number 4. What do I say? I think this one is obvious. The reason is 0 is not in there. So 0 is not in this. there is no way you can get 0. That's why it's not a field. Well, it doesn't have, it failed a few axioms, I think, but the most obvious one is 0 is 9 there. There is no way you can get 0. Oops, it's now. This, it's multiply them together. Okay. And the last one is a field. You can check all of them. So this proof, I'll leave it to yourself. This proof is just check all of them. Like for example, let me give you like an example to show Q is a field. Oh no. Did I lose some part of my work? Zoom is crashing. Don't know if I recorded everything before. I hope so. Don't want to go do it again. Anyway, what I just said is Q is a field, and this is how you can check. For example, maybe I'll check one for you. Maybe I'll check closure for you. Okay. So for any element in Q, you can write the elements as, you can write them as, let's say, m over n, right? So x plus y, so I'm gonna let m over n or a over b in Q, where my m and a, b are integers, and b cannot be 0. Maybe I'll add a restriction that it's a, they are in the lowest term. And the b are in lowest term. Then I can add them together. So m over n plus a over b is adding them together. This will give you mb, and top is mb plus am. This is an integer. This is also an integer. And also this is definitely not 0 because n is not 0, b is not 0, which means the whole thing is still in rational number. So it's closed under addition. This is how you prove the first one. And you do the same thing for this, and similar things for the rest. Pretty sure you know how to do it now. Try to prove yourself.